Hello, ladies and gentlemen. So today, what I want to do is I wanna briefly try to find the area of a triangle using a Riemann sum. Okay. Now, of course, we could do this problem in general for any triangle, but to make our lives easier, I'm just going to use a right triangle. Okay. So let's pretend that we have a right triangle. Okay, like this. Let's say that the distance here is 5. And let's just say that the distance here is, let's say, 4, something like that. Okay. So basically, obviously, you can see from my drawing that that what I want to do is I want to superimpose the x and y axis so that they line up against this side of length 4 and this side of length 5. Okay. And my purpose for doing so is that I want to represent the hypotenuse of this right triangle with a function, right? So if this length is 5, I want you to notice that this length would have to be 5 also, which would mean that this point, I want you guys to think about what it should be before I tell you. This point should be 5, 0. And by the same kind of reasoning, I suspect you all are beginning to imagine what this point should be. What should this point be if I've superimposed, or if I have placed this here on the y-axis? I think all of you would agree that the point should be 0 because it's 0 along the x and 4 along the y. So I have now, and of course, the fact that the x and y axis are perpendicular uh, gives us our right angle. Now, some of you may have already noticed, well, David, just to be completely technical here, this triangle, I can flip it around like this, and in that case, wouldn't it be possible, you guys might ask, for us to place the triangle like this, with this having length 4, in other words, the side that's vertical there being placed along the x-axis, leaving this point to be 4 comma 0, and placing that side with length 5 along the y-axis, leaving this to be the point 0, 5, and couldn't we use this triangle, or couldn't we use this representation to find the area of the triangle using a Riemann sum? And the answer to that is yes. But for right now, we're going to look at it from the perspective um, of using this drawing. But yes, this would be totally acceptable. And of course, you can also think that you could rearrange this in different ways. We could rearrange it like this, where this is 5 and this is 4, just by reflecting it across the x-axis. Or by the same reasoning, like this, where it's 4 here and 5 here. Each of these triangles having the same area. Okay. Okay. So in other words, if we want to find the volume or the area of like the measurement of some kind of geometric object, and we know that that geometric object has some particular symmetry property, then yes, there will be different ways of us the writing down the representation, let's say, in a Cartesian plane, such that we can solve the problem. Okay. So now that we've been able to superimpose our beautiful geometric object, which exists only in our brain as a perfect geometric object, onto our xy plane, which of course in this case is also an idealization, right? We only know this for real in our brain. Um, okay, that's kind of a joke, okay? But anyway, we now have a realization of our geometric object onto our Cartesian plane. What do we do now? Well, in this case, this function for this top is simple. It's just a line, right? And we first, to find the equation of the line, we're going to do two things. We're going to, number one, find our slope. Now, some of you may already have figured this one out already, but just for the sake of discussion, let's just do it explicitly here. We know that the slope of the line joining two points with coordinates x1, y1, and x2, y2 will be given by y2 minus y1 over x2 minus x1. And therefore, in this case, let's say I choose this to be my y2. So 0 minus 4 over 5 minus 0. And so our slope will be m equals negative 4 over 5. Because 0 minus 4 is negative 4, and 5 minus 0 is 5. You guys with me? Yeah. Hang on. So now we know our slope is negative 4/5, right? And so now what we're going to do is we're going to make the equation in line to this point. If you all know the equation, and I know you guys all do, that y equals mx plus b represent where m represents the slope and where b represents the y-intercept, we can see here that our y-intercept is 4. So we can very easily just use this equation to write our equation. So y equals negative 4/5, the slope we just found, x plus 4. So this is our equation. Okay. So now let's proceed from here. This is our equation. This is our drawing. And now we're going to do the Riemann sum. So our equation we know is y equals negative 4/5 x plus 4. And we know that our graph looks like this. This is 5, 0. This is 0, 4. Right? Okay. So what I want to remind you guys of is, what is the Riemann sum idea? The Riemann sum idea is that we take some slice of this interval, like let's say I cut it here, and I now want to approximate the region by rectangles. So for example, a so-called right hand Riemann sum will take the end of the rectangle, the height of the function at the right end of the rectangle, and use that as our estimate. In this case, if we were to slice this region from 0 to 5 into two rectangles, let's say evenly, slicing in the middle here at 5 over 2, 2.5, the height at 2.5, which would be the right-hand endpoint, would be here. So we would cap that off here. And then at this endpoint, the height would be 0. So the right-hand rectangle, if we sliced it like this, would just be, would have 0 height. So the estimate would be the area of this rectangle plus this rectangle. But since this rectangle is flat, it has area 0. And this rectangle has width 5 over 2. And it has height, we could plug that in here. Y equals negative 4 over 5 times 5 over 2 plus 4. You can see that 5 divided by 5 cancels. Negative 4 divided by 2 is negative 2. So negative 2 plus 4 is 2. So this height would be 2. And so if I were using this, if I were estimating this area by just this rectangle plus this rectangle, again, this rectangle is 0, then basically it'll be the length times the width, or the base times the height. So 5 over 2 times 2 has an area of 5. Okay, now obviously this would be an underestimate. Now let's look at that again. Let's imagine I have my figure. Let's say this is 5. And let's say I slice it into 5 pieces, just to get an idea. 1, 2, 3, 4, and 5. I'm going to draw my vertical lines here. If you were on paper, you could draw this super pretty with like a very light pencil, just to make sure your drawing comes out super nice. Now let's just say, for the sake of discussion, that in this case I want to make a left-hand Riemann sum. So what that means is I'm going to take the height at my left endpoint to represent the height of the rectangle of each rectangle. So this first rectangle, right, the height will be here if I do the left-hand endpoint. If I use the left hand, in other words, this would be the left-hand Riemann estimate, right? I'm taking the left-hand side of my interval, of my subintervals, to determine the height of my approximating rectangles. That's why it's called the left-hand endpoint. I mean, that's why it's called a left-hand approximation. Just a little side note here, which I'm not going to go into right now, but I want you to observe that in this case, this function is decreasing. We know that because it looks like we're going downhill. We can also look at it because the slope is negative, so that means every time we move to the right, we're going down. And so it makes sense in this case that the value of the function on the left-hand endpoint for a decreasing function like this will be bigger over that subinterval. That means that in this case, the left-hand Riemann sum is an overestimate, right? Okay. And of course, if the function was increasing by a similar sort of argument, the left-hand Riemann sum would be an underestimate, because if the function were increasing, then the value on the left-hand endpoint of each rectangle would be the minimum on that subinterval. Okay? And you could easily see from here how we could calculate the estimate. We would take these widths and we would multiply them respectively with the lengths, well, in this case, the heights, right? And then we would add them up. So let's look at that together. So in this case, I don't know if you've noticed this, but in this case, I've divided up the widths evenly. In fact, I want you to notice that I use the formula, in this case, delta x, which we're going to use to represent the width of the intervals, as b minus a over n, and in this case, 5 minus 0 over 5. 5 because it's this 5 on top, this 5 minus 0 is this 5, which is the b of the interval, and the 0 is the a of the interval. And 5 down here in the bottom because it's how many rectangles I'm forming. Okay? You can see that in this case, each interval has width 1. They don't all have to have width 1. That's not a requirement. If I wanted to make a Riemann sum with intervals that were of varying widths, that's also possible. But for our calculations, we're going to do them with even widths just to make it easier. Okay, but again, like I said, it's not necessary. And then we can calculate the height at each of these points. So let me do that real quick here. If I'm at 0, we know that the value of the function here at this value, if x is 0, this goes to 0, so we're left with 4. So I'll put that here. So x and then the height. We just found that at x equals 0, our height is 4. At x equals 1, our height will be negative 4/5 plus 4. And just to make our lives easier, I'm going to rewrite this function underneath, but with 4 written as a number as a fraction with a 5 in the denominator. I ask myself, what is 4 times 5? I know that 4 times 5 is 20. So I know I can rewrite this as negative 4/5 x plus 20 over 5. 20 divided by 5 is 4. So this equation is the same as this, but it'll be easier to calculate the numbers I need by writing it like this. See, because if x is 1, 1 times negative 4/5 is negative 4/5 plus 20/5 is 16/5. We know that this is approximately 3.2. 1, actually, it's exactly 3.2. If I plug in 2 for x, which would be the height here, that'll be negative 4 over 5 times 2 is negative 8 over 5 plus 20 is 12 over 5, which is approximately equal to 2.4. Okay. If we plug in x equals 3, the height of this rectangle, 3 times negative 4 is negative 12 over 5. Negative 12 over 5 plus 25 is 8 over 5, which is 1.6. And then at 4, which is the final one we're going to have to calculate because we're doing the left-hand estimate. So we got the 0, the 1, the 2, the 3, and now we're going to get the 4. negative 4 over 5 times 4 is negative 16 over 5 plus 25 is 4/5. And that's, of course, approximately 0.8. Well, actually, these are not approximate. These are exact values. I can show you that later. And now let's calculate the left-hand Riemann sum. So it'll be, we'll call this, oh, actually, we don't have to name these, okay? I'll just write them down over here. So the left-hand Riemann sum is going to equal, the first rectangle will be this rectangle. It has width 1, as we mentioned above, and it has height 4, right? We can see in our table. Plus, notice, how am I getting the area of these rectangles? These approximately rectangles, it's the width times the height. So the second one is going to be 1 plus, it's going to be 1, the width at the bottom, times the height, which is 16 over 5, plus the width of the third rectangle, which is going to be 1 again. Again, we chose these to be evenly spaced, times the height, which at this value is 12/5, plus, again, the width of 1 times the height, which is going to be 8/5, and then plus the width of 1 times the height of 4/5. Now, of course, as it turns out, these are all in terms of fifths, so it's easy to see what they're going to calculate to, or what they're going to add up to. They're all addition, they're all times 1. So basically, and we know that 4, from the same argument we gave here, is 20 over 5. So 20 over 5 plus 16 over 5 plus 12 over 5 plus 8 over 5 plus 4 over 5. Okay? We can just add this up. 20 plus 16 is 36, 48, 56, 60 over 5. We're claiming that this estimate so far is 12. Okay? And let me just do that real quick here, just so that we don't make any mistakes. I'm going to redo that by hand here. 4 plus 8 is 12, 13, 14, 20. 2 plus 2 is 4, 5, 6, 60, right? So this is correct. Okay? So in other words, what we just did there is, if we do the Riemann sum with 5 rectangles, we added up, and of course the left-hand Riemann sum, because we used the height at the left of the intervals, we got this estimate. All right? And of course, for reasons we discussed earlier, we know it's an overestimate, but that's how we do it. But now I want to do something more interesting than that. Let's go further. Let's ask the question of what happens if we let the number of slices be arbitrary. In other words, we let the situation be n slices, and then we figure out what happens when we let n go out to infinity. Okay, in other words, we let the width of the intervals and of the slices go to 0. Okay, so let's look at that here. Okay, so we have our graph again. Okay, and in fact, here I want to make this graph very carefully, and I want to make it bigger so you guys can see exactly what I'm doing here. And by the way, one of the things I want you guys to know about why we're doing it this way with this very simple function for the moment is that I want to have one bit less of complexity when we're doing this problem. Okay? But the procedure will work for any continuous function that we can do. Okay? So now I've drawn my figure large, as we mentioned earlier, because I want to make the argument I'm about to make as clear as possible, because this is the crux of the magic. So let's pretend, again, this is x equals 0, right, this location, and this intersection of the corner of the triangle, at least as far as we've drawn it, has been 5. Of course, if you guys were to have oriented the triangle differently, as I hinted at earlier, the endpoint here would have been different. Okay. Okay. So now here's the idea. we want to find the Riemann approximation, the Riemann sum approximation, but we want to do it for arbitrary many rectangles. So our A and B of our interval is still 0 to 5. Okay, right? Our interval AB, over which we're trying to find this area, is still 0, 5. So that means, you can see it here, so that means that the width of the interval, the delta x, is still 5 minus 0 over n. 5 minus 0 is 200. Okay, 5 minus 0 is of course 5. So this is 5 over n. Okay, you guys with me on that? Okay. So now here is where it gets interesting. This is where this is different from what we did before. Let's pretend we're here at 0. We're going to walk this way, but with footsteps, let's say, of length 5 over n. So what's 0? Of course 0 is 0, right? No surprise there. Wait, is 0 100? No, I'm just kidding. Okay, 0 is 0, of course, right? If we take one step of 5 over n this way, then we're at 5 over n. Now, if we take another step of 5 over n in length, then that's going to be 5 over n times 2, okay? Now you might say, okay, David, prove it to me, right? Okay, so 0 was our starting point. We took one footstep of length 5 over n, so that's 0 plus 5 over n. That's how we got here. Then 0 plus 5 over n plus 5 over n. Now, if we remember, if we go back in time to when we were learning about multiplication, we could see multiplication as repeated addition. Obviously, we also have the area model for multiplication, right? But for right now, if you think about the repeated addition model, that is to say, let's say 2 times 3, what is 2 times 3? It's either 3 plus 3, because we added the 3 2 times, or it's 2 plus 2 plus 2, because we added the 3, because we added the 2 3 times, right? In this case, you can see that plays perfectly here. 0 plus 5 over n plus 5 over n is 5 over n times 2. And of course, you guys can already see the picture here, right? We're over here. If we take our third step, we know it's going to be 5 over n times 3. Now, in this point, I'm going to put dot, 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 because obviously there's n rectangles. What if this n is just 2? Then, obviously we can handle it. We saw that before. But what if n was 100 million? Or what if n was some large number? Then there's going to be a lot of steps in here, right? So I'm going to put the dots to represent that. Okay, now let's look at this right-hand side. Now I know what you guys are thinking. You guys are thinking, David, why are you going all the way to the right? Right? Why do we want to look at this endpoint? And you're going to see why in a moment. Okay, now I want to ask you guys a question. And I want you guys to imagine, if we keep going in this direction, what times 5 over n will give me 5? What times 5 over n will give me 5? Okay, so let's figure that out. 5 over n times something, let's call it x, equals 5. I want to find out what this x is. So what I'm going to do is I'm going to multiply both sides by the reciprocal of 5 over n to isolate the x, right? Here, the n's cancel, the 5's cancel, and I'm left with x. Here, the 5's cancel, I'm left with n. Now, of course, looking at it that way, it makes sense. We can see that 5 is the same as 5 over n times n. And the reason why I really wanted to show this to you here, first of all, I wanted just to remind us how we can think about that, but also because I want to know the penultimate point. If this is 5, if going from this direction, 0, 5 over n, 0, 5 over n, 5 over n times 2, 5 over n times 3, if we're adding 5 over n, then from here, notice the one that would be here, 5 over n times 1, 5 over n times 2, 5 over n times 3. Then if this one's times n, then the penultimate one will be 5 over n times n minus 1. Okay. And now, and let me just plug that in here. Even though we don't need it here, I'm going to put in the 1 here so that we can see the pattern more clearly. Okay. So now with this setup, okay, and I recommend you always to draw this setup when you're doing your paper. Obviously, the graph doesn't have to be that pretty. The prettier it is, it may look nice, but the main idea is you have to do your drawing. You draw your our partition. Let's call well. This is not the partition, but these are like the values that are going to compose the partition, right? Our partition is just like the slicing up of our interval into pieces, the endpoints that we're going to use, and the points where we're going to test. So let's just suppose, for example, that I want to do a left-hand Riemann sum. So to do that, I would need to know the left-hand endpoints, which we're going to represent as LHE. Okay? I want you guys to see this very carefully. So let's now imagine in our brain that we're slicing. This triangle is actually secretly cake. So we're slicing it with our cake knife like this so that we can take our pieces from it, right? And so if we want to do a left-hand estimate and we get the extra part as cake too, then we're getting more cake than we actually have. Okay, that was a joke. But we slice it vertically like this to get our rectangles. Let's say we want the left-hand endpoints. Let's look at this carefully. The first left-hand endpoint will be in this case 0. Okay. For the second rectangle, the left-hand endpoint is 5 over n times 1. For our third rectangle, our left-hand endpoint is 5 over n times 2. For dot dot dot, boom boom boom. And then our final rectangle will be this one. So our final left-hand endpoint would be 5 over n times n minus 1. Okay. By the same reasoning, we could list our right-hand endpoint. Okay. If we look at our first rectangle, our right-hand endpoints would start. Our first rectangle would have right-hand endpoint 5 over n times 1. Our second rectangle would have right-hand endpoint 5 over n times 2. And our final rectangle would have right-hand endpoint 5, right? Or in other words, as we saw earlier, 5 over n times n, okay? So now I'm going to shrink this drawing. Well, actually, do I have to shrink it? No, we don't have to shrink it. We'll just go with it. Okay, we'll just go with it. And remember that this function here is given by, in other words, this height is given by this y equals negative 4x plus 4, which we're just going to represent here for the time being as f of x. Okay, like this. Beautiful. Okay. Okay. To represent the height as f of x before I actually plug it into this function. Okay. Okay. So just for the sake of discussion and for concreteness, I want to do a left-hand Riemann sum. Okay. And one of the things I always tell my clients to do whenever they're doing a left-hand Riemann sum is to write out the terms just like you would normally. In this case, the width of the rectangle is 5 over n. Okay. So our left-hand Riemann sum will be 5 over n for the first rectangle times the height of the first rectangle. Okay. Now in this case, the height will be the function value at 0 because we're doing the left hand. So for right now, I'm going to write that as f of 0. Okay? Okay. Now let's do the second rectangle. Plus the second rectangle will again have a width of 5 over n. Okay? But the height will be f of the left-hand endpoint. What's the second left-hand endpoint? 5 over n times 1. And then plus dot dot dot. And notice, the left-hand endpoints are the ones I'm using here. 0, 5 over n times 1. The next one will be 5 over n times 2. And then the final one would be 5 over n times n minus 1. So actually, let's do that a little bit more carefully here because I want to make sure that we see the pattern. So again, the width of each of these rectangles, by design in this case, was 5 over n. The height of the third rectangle, as we just mentioned, is the third element of our left-hand endpoints, which is 5 over n times 2, right? And then plus, and then dot, 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 plus the final rectangle, which will have width 5 over n, and which will have height. Remember that the final left-hand endpoint is 5 over n times n minus 1, right? I think we can get rid of this drawing now. I think you guys see where I got all these values, right? Let me just walk you through it here. 5 over n was the width of the rectangle, of this first rectangle, and the height was the function value at x equals 0, the left-hand endpoint. That's why we're calling it a left-hand Riemann sum. If it had been a right-hand Riemann sum, the height would have been at the right-hand rectangle, okay? So let's delete this because we're about to do some magic, okay? Okay. What I want you guys to see here is this underlying pattern. This is 5 over n times 1 for the second term, 5 over n times 2 for the third term, 5 over n times n minus 1 for the last term. This one is 0, but we could write that as 5 over n times 0 if we want to keep this pattern. And so what I want you guys to notice is I can rewrite this expression as, and I'll factor out the 5 over n out of the whole expression, since each term is being multiplied by 5 over n. So I can have 5 over n times f of, let's say, 5 over n times 0 plus f of 5 over n times 1 plus dot 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 plus f of 5 over n times n minus 1, okay, like this. And now look at that pattern, 0, 1, dot dot dot, all the way to n minus 1. So I can now compress this down to a summation. So I'll put my 5 over n is the sum from k equals, in this case, from 0 to n minus 1 of the f of 5 over n times k, okay? I want you guys to see how this is represents this. See, when k equals 0, I get f of 5 over n times 0, which is exactly this. And of course, it's being multiplied by 5 over n because each term is being multiplied by 5 over n. By the way, yeah, that's number 1. When k equals 1, I'll get this term. When k equals 2, I'll get the third term that's missing here. And when k finally equals to n minus 1, I get the final term, and it terminates there. Okay? Now that I've written it like this, I can plug in to my formula. What is the f of x? F of x is negative 4/5 x plus 4. So this is 5 over n times the summation k equals 0 to n minus 1 of negative 4 over 5, 5 over n times k plus 4. Okay? So this is now getting to the point where I can actually evaluate it. So I'm going to copy this over here so we can actually do the evaluation. So let's copy that over here. This is 5 over n summation k equals 0 to n minus 1 of negative 4/5 times 5 over n times k plus 4. So the first thing I want to do here is I want to simplify this algebraically inside. You can see here that these 5's cancel, and we're left with negative 4 over n k 4. Okay? Okay, so this is 5 over n times the summation from k equals 0 to n minus 1 negative 4 over n times k plus 4. Okay. Now there is a rule, and it says that the summation of a plus b, or ak plus bk, is equal to the summation of a sub k plus the summation of b sub k. Okay? So in this case, I can do that. I can break this as follows. This will be 5 over n times the summation from k equals 0 to n minus 1 of negative 4 over n times k, and then plus the summation from k equals 0 to n minus 1 times 4, or of 4, right? Like this, right? Okay. Okay. So now we're almost there. Let's look at this together. Okay. Now check this out. What I want to do now is this. What I want to know, well, let me see here first. Okay. So now first, I want to point out that this negative 4 over n, it does not have any relation to the constant k. So it's actually, or it has no relation to the index k. So this negative 4 over n never changes um, as k changes. So it can be factored out. Okay, and this can also, this 4 can be factored out, or we can handle that in a different way. Okay, so what I'm going to do here is I'm going to write down what the next step is, and then I'm going to calculate the different pieces individually. Okay, so this is going to be negative 4 over n times the summation from k equals 0 to n minus 1 of k. And then here, this is just going to be plus the summation of k equals 0 to n minus 1 of 4. Okay. And now here, we actually kind of ran into a slight difficulty here, which I'm going to show you. Okay. So first of all, we're going to need to know some facts. So I'm going to first do this sum. Oops. Oh, whoopsie. Okay. I'm going to first do this sum here. We're going to call this A, and then we're going to call this B. And once we've done them both, we'll add them. Okay? Okay, so I want to look at the summation from k equals 0 to n minus 1 of k. Now let's look at what this gives us. If k equals 0, this is 0. Plus, if k equals 1, it's 1. Plus, if k equals 2, it's 2. Plus, dot, dot, dot. And then it stops when we get to n minus 1. So plus n minus 1. Okay? Okay. Now it turns out that the sum from k equals 1 to n of k is actually n times n plus 1 over 2. This is a famous formula, and it's one that you should learn. Okay? So if you notice, if we look at this, notice how this first term is 0, so we can just chalk it. So this is actually the same as k equals 1 through n minus 1 of k. Okay, I really shouldn't have used the same letter here. I should have used like maybe j here instead. Okay. But I think you guys can see that this is the same as this, because if you look at it, the 0 makes no difference. So if I start with j equals 1, I get 1. When j equals 2, I get plus 2. When j equals 3, I get plus 3. And then I stop when I get to n equals 1 to n minus 1. But now notice in here, it's in the same form as this. So now I can plug into this formula, which tells us that, so the top limit is n. So it's going to be n times n plus 1 over 2. The top limit here is n minus 1, so it'll be n minus 1 times n minus 1 plus 1 over 2. So n minus 1 plus 1 is just n. So this ends up being n, this n, times n minus 1 over 2. Okay? So let me write that down here. So this is going to be 5 over n from here times negative 4 over n from here times n times n minus 1 over 2 from here. Okay? And now we're going to do the next one. Okay? Okay. Okay. So let's ask ourselves what the sum from k equals 0 to n minus 1 of 4 is. So this, if we think about it, it's when k equals 0, this is 4. So it's 4 plus. When k equals 1, this is still 4. 4 plus dot dot dot. And when k reaches n minus 1, it's again 4. So now what really is happening here is we want to figure out how many terms there are from 0 to n minus 1. So let's think about that. Let's pretend that n were equal to 5, just for the sake of discussion. Okay? And I listed from 0 to n minus 1, which would be 4. So 0, 1, 2, 3, and 4. From 0 to n minus 1. I count them. 1, 2, 3, 4, 5. So there's 5 terms. In other words, here I'm claiming that there's n copies of 4 being multiplied or being added, right? N copies. Okay. Now, of course, you can see from here that the argument is exactly the same in the general case. If n were to equal to n, then this is obviously yeah, you can see where I'm going with this. Then the listing would be 0, 1, 2, dot, 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 all the way to n minus 1. And so all we can do is we can just attach this 0 at the end to count them, and we can see 1, 2, all the way to n minus 1, and then one more, which is the 0. But you could just look at it like this as well, right? We can see this as being 1 through n, shifted to the left 1 unit. So these are different ways of seeing that in fact it is in fact n copies. Okay, now here if you have if we have n copies of 4 being added, what is that? That's 4n. So then this term here is 4n. Okay, so plus 4n, like that. Okay, okay. So now we are ready to look at what this gives us. So this is 5 over n times, we'll just put that in the up here, 4 over n times n minus 1 over 2 plus 4 over 2 plus 4n. Okay, let's get rid of this now. Now here, you can see that this will cancel with this, okay? And this will become a 2 here. Well, actually, I don't want to cancel it like this. Let me just rewrite it properly. Yeah. Okay. So let's say 5 over n times 4 divided by 2 is 2, so this will be negative 2. These n's will cancel, quote unquote, cancel. We'll get n minus 1 plus 4n. Let me just double check that before we move further. This n's canceled. This became a 2. This is negative 2n minus 1, blah, blah, blah. Okay, that's right. Now let's go over here. Now look at this. Let me write that down here. 5 over n, negative 2n, plus 2, plus 4n. So if you notice, this thing gives us 5 over n, negative 2n plus 4n is positive 2n, and then plus 2 right? Because of this 2 in the middle. And then we can now distribute in the 5 over n. 5 over n times 2n, the n's will cancel, we'll be left with 10. And then 5 over n plus 2, right? Or 5 over n times 2 is plus 10 over n. Okay? Okay. So look at what we got here. After all that work, this is our left hand Riemann sum for n rectangles. Okay. We simplified it to that simple expression, 10 plus 10 over n. And I want to observe several things here. First of all, remember early on that when we were looking at this situation, we said that this function is decreasing, right? So we knew that the left-hand estimate was going to be an overestimate, right? And you can see here we have 10 plus some positive number. Now, check this out. Where did this n come from? This n came from how many rectangles we were going to have. If we let n go off to infinity, if we let n get larger and larger and larger, that means that the width of these intervals is getting smaller, right? Because the width of these intervals is 5 over n. So as these intervals get smaller, we expect the estimate to get better. And in fact, in this case, we can see that as n goes to infinity, the 10 over n goes to 0. And so we're claiming that the area of this triangle is actually 10, right? Because 10 plus a number that goes to 0 is 10. Okay, area is 10. Now, is that in fact the case? We remember our triangle, where we all started this, was 5 on the bottom and 4 on top. We know that from geometry, the area of a triangle is 1/2 base times height. The base is 5, the height is 4, 5 times 4 is 20, 1/2 of that is 10. So, in fact, the answer we just got is consistent with the area that we expect to get from geometry. So that just means that we have taken an age-old problem that was easily solved and have complicated it to the point where it now took us like an hour to do it. That's of course a joke, right? But it's nice to see how this process, this procedure, can give us results that we know from the past. It helps our intuition accept, you know what, this is giving me what we expect to get. It actually did give me the area of a triangle. And of course, this is an incredibly important tool. Of course, by the way, I also want to point out, you're not going to have to calculate all of the integrals like this. I mean, that would be crazy. But it's nice to show simple examples like this, relatively simple examples like this, so that you can see how the Riemann sums actually work and how they actually give you those results. And of course, later when we learn the integral rules and all that stuff, we don't have to do all these calculations. But it's nice to see how it works. And if you guys want to practice, you guys can do the right-hand estimate. Yes. Anyway, I hope you enjoyed this example, and I wish you a great day, and I hope to see you again. Thank you.